Swayam Prabha. Digital India. Educated India.
Please take a notebook and please write. So you see, I wanted to explain a few things in connection with evolutes and involutes, okay, and I have written them down for myself here. So the first thing is the, is the following statement, namely the evolute of a curve is singular at each point where the curve has a vertex. Okay, so here is the first instance where we are formally looking at the idea of what is called a vertex. Okay, and see, by definition, the vertex of a curve is a point at which the curvature function has a critical point. Okay, that means the derivative of the curvature function vanishes. All right, and see, we always assume that the curvature function is at least continuous. Okay, and if you assume the curvature function is also differentiable and continuously differentiable, okay, then you see where the curvature function has a critical point, okay, that is where the derivative of the curvature function vanishes, that is going to be a vertex for the curve. Okay, and of course, you see, for defining the curvature you need the second derivative. Okay, and you, as it is assumed that the second derivative is continuous, because it's our policy to assume that whenever a certain derivative exists, then it is continuous. Okay, but you may also have to differentiate the curvature function, okay, if you want higher derivatives. Okay, because you see, the Frenet-Serret frame involves the derivatives of the the Frenet-Serret frame itself, namely the unit tangent and the in the case of plane curves, it is the sine normal. Okay, of course, in this case of space curves, you will have the principal normal and the binormal also. Okay, but we are looking at only plane curves. So you have the derivative of the unit tangent, you have the derivative of the sine normal. All right, and that involves the sine curvature, that, because that's how the Frenet-Serret matrix is defined. Okay, it's a skew symmetric matrix, 2 by 2 matrix, with the top right entry being the sine curvature. Okay, and the diagonal entries are 0, and the lower left entry is the negative of the sine curvature. Okay, if you want to get further derivatives, let us say second derivatives of the unit tangent and normal, then that is the sine normal, then you see it will involve the derivative of the curvature vector. Okay, I mean, it will involve the derivative of the sine curvature. Okay, and then it makes sense to take that the sine curvature itself is continuously differentiable. Okay, and in that situation where the derivative of the sine curvature vanishes is going to be a vertex for the curve. So if you look at the evolute of a curve, so that is something that we have already looked at. So let me show this thing here. See, so you see the evolute of the curve. This is the formula that we have written. Okay, this is the position vector of the evolute of gamma. Okay, where gamma is unit speed parameterized. So the evolute is is given by gamma plus you move along the geometric normal, okay, towards the center of curvature by a length which is equal to the radius of curvature, and the way we write it is the radius of curvature is reciprocal of the magnitude of the sine curvature, and the sine is of course put so that you compensate the direction of the sine normal, okay, so that this product always points towards the center of curvature. So this is the formula for the the evolute of gamma, okay. Mind you, the evolute is the locus of the centers of curvature. Now we computed that when you take the derivative with respect to s, okay, then you get we have to use the Frenet-Serret relation, okay, and then the gamma dot term cancels out. All right, gamma dot, mind you, is t cap gamma. It is the unit tangent vector. So what is left out is only the unit normal vector, which is of course the sine normal, okay, and you get this coefficient here. And look at that coefficient. See, for a curve to be regular, okay, its tangent, the velocity should never vanish. Okay, that means the tangent vector should never vanish. So if epsilon sub gamma is the the evolute of gamma, then this is the tangent vector epsilon sub gamma dot, and you see that there is this coefficient here. That coefficient should not vanish. Okay, and that coefficient, you see, that means what? First of all, the denominator should not vanish. So the curvature should be not zero. The sine curvature should not vanish at that point. And then you see in the numerator, you are getting this derivative of the curvature, the sine curvature. And therefore, you see, if the derivative of the sine curvature vanishes, okay, then the right side is 0, and therefore the left side is also 0. That means that the evolute is not regular. Okay, for regularity you need that the tangent vector does not vanish. You need the velocity should not be 0. Okay, so what I want to tell you is that the points where the curvature vector has 0 derivative, namely these are the critical points of the curvature vector. These are exactly the points where the evolute will have irregular points. Okay, and the points where the the curvature has critical points, okay, these are called vertices of the curve. Okay, and these are important because they effectively tell you that the curve is as it comes towards that point and leaves that point thereafter, it is actually making a turn. Okay, and then we will see later on this global theorem, which is the 4 vertex theorem, which will tell you that if you take a simple closed smooth curve, then it should have at least a minimum of 4 vertices. Okay, so you will see that these vertices are important. But therefore, let me make this statement here. So note that for the evolute to be defined and regular, we need that the sine curvature should not vanish, and the sine curvature should not have a critical point. And a critical point of the sine curvature is called a vertex of the curve. Okay, okay. Therefore, the moral of the story is that at all the points where the original curve has vertices, okay, the evolute will have singular points. Okay, it will not be regular. the evolute, its evolute has a singular point, that is its evolute is not regular. Okay, so this is something that that is the first thing I want to tell you. So then the next thing I want to say that of course is this thing, for defining the evolute, the curvature should not vanish. That is again something that I just now told you, namely you look at this formula here, the velocity vector of the evolute is, you know, as a regular curve. If you want it, then this coefficient should not vanish, and in the denominator you have the, you know, sine curvature, square of the sine curvature, and that should not vanish. Okay, so we need that, and so that is the next fact. Okay, then there is this business of, you know, taking a curve, okay, finding its involute, finding any of its involutes, and then taking the evolute, okay, and you get back the curve. Okay, now this is this can be I've already told this can be done geometrically. You can also see it analytically. Okay, so I want to explain that. So let us look at this situation. So we have this kind of a so this is a curve, this is gamma of s. Okay, and let me take some point here which is, you know, this corresponds to s equal to 0. Okay, and so this is gamma 0 if you want. Okay, and then what you do is that you take a string of length L, okay, on the curve from here to some point here. So gamma of 0 if you want is p0, and then this length is L. Okay, then I get this point if you want q, q0. All right, so then what you do is that, you know, you gently pull this string out. Okay, you pull the string out and then you trace a curve like this. Okay, and so basically what happens is that when you have pulled it out completely, you know, then you get this, you will get this kind of a picture. So you will get this, so let me draw it like this. Okay, and so when you pull it out completely, you are going to get this point, if you want, let me call it as q1. All right, and this length will be L. Okay, and this curve that you pulled out, okay, is exactly the involute of gamma with this choice of point p0, where I have fixed this string. Mind you, this other end q0 is free, which I am pulling it out. Okay, and then this length of the string that I have used is L. Okay, and this involute, what you see from this involute is that, you know, at so there are so there is already something that is geometrically very clear. If you take any point here in between, okay, with arc length equal to, let us say, s, okay, then, you know, at this point you draw the tangent to the curve. Okay, then this this length will be the same as this length that is remaining. Okay, so this will be L minus s. Okay, and then you know how to reach this point. All right, this point, if you write the equation for this point, you are going to get, you know, so this I gamma p naught L at if you want to call it at s, this is going to be, I have to go first, the position vector is the starting position vector, okay, plus L minus s times this vector, okay, which is the tangent vector, okay, at that point. So you take the unit tangent vector at that point and multiply by L minus s. Okay, so what is it going to be? It's going to be, so I have to write gamma of s, okay, plus L minus s times, you know, I have to write t cap gamma sub s. Okay, so this is the equation of the involute. Okay, and of course, this involute depends on these choices. I have to choose this point P naught where the string is fixed, and I have choose this point Q naught, and which depends on the length L of the string that I have imagined on the curve, and then I am pulling it out. Okay, now actually the way this is the way this is written. Okay, what I want you to see is that either you can think of as the string being pulled out or unwound, okay, or if you do it in the other direction, it's like the string being wound. Okay, so you start with either you start with the string at on P naught Q naught, and then you pull it out, okay, and you end up with P naught Q1, okay, which is the full length pulled out, or you start with P naught Q1 and you wind it on to the curve. So you can either take it as an unwinding moment or as a winding moment. All right, and see what you can see at every point of the at every point of this involute is that you see if I draw a picture, then you see here you see this direction here by this red arrow. This will be the tangent unit tangent to gamma. Okay, let us assume that gamma is unit speed if you want. Okay, so this will be the unit tangent to gamma, and you see this guy here, I mean at this point, okay, this is the involute. If I draw, you see the way the if you look at the direction in which the involute is being traced as s goes from 0 to L. Okay, so what happens at s is equal to 0? You see, at s equal to 0, this is I gamma P0 L of 0 is gamma 0, okay, plus I'll get L T cap gamma of 0. Okay, so this is, you see, this is this vector basically. S equal to 0 corresponds to this. Okay, and this is just I'll call it as what is it? This is a P. It is P0Q1 vector. This is the vector. All right, and as s increases, actually the if you want the right direction, it is actually a it is a you are winding the string onto the curve. Okay, so let me and that is very important is because I want to keep track of the unit tangent to the string. Okay, and the unit tangent depends on the orientation. The unit tangent of a curve depends on the orientation of the curve. If you change the orientation of the curve, then the unit tangent changes. I want to keep track of the unit tangent of this involute. Okay, so what I'll do is let me remove this arrow and put the arrow like this. Okay, so if you put the arrow like this, which is the correct direction, which means that now it's like you're winding the string onto the curve. Okay, then at this point you see what will be the unit tangent to the to the involute. This will be T cap of I sub gamma. Okay, if I call this as simply I sub gamma and forget the choices P naught and L, I suppress those choices. So this is T cap. All right, and then this angle is 90 degrees. See, what you can see immediately is that you see the unit tangent to the original curve, okay, is in the normal direction to the involute. Okay, and for that matter, what is the sine normal? The sine normal will be like this. So I will have to take the unit tangent of the involute, and then I have to rotate it 90 degrees anti-clockwise direction. That in the anti-clockwise direction. So I'll get something like this. So I have to move like this. Okay, and this will give me this will give me the ns. This is the sine normal of I gamma. Okay, this is what I'll get. And you can see what you can see from the picture is that the this unit vector is exactly the same as the the unit tangent of the curve. Okay, so from the picture you can see, and you can verify this analytically also, that the T cap gamma is exactly ns hat I gamma, okay, all right. And what about what about T cap of I gamma, the unit tangent vector of I gamma? You can see that this is going to be negative of the sine normal of gamma. Okay, so where is the sine normal of gamma? If I have to draw something like this here, okay, and this is so I rotate 90 degrees the unit tangent. So this guy is going to be the sine normal of gamma. Okay, and you see that this vector here is opposite to this vector here. Okay, and therefore you also get from this that T cap of I gamma is actually negative of ns hat of gamma. So you get these two relations from the picture, okay, and of course these two relations can also be proved analytically. So you can do that, okay, but what I want to say is that from this what I want to say is that you start with gamma, you take an involute, you end up with I gamma P naught L. So this involute depends on the choices of P naught and L. Okay. Then what you do is now you take the evolute, and lo behold, you will get back your gamma. Okay. And what is the reason for that? So there are two ways to look at it. Geometrically, okay, taking the evolute means that you are taking the envelope of the normals. Okay, but you can see from this picture clearly that the normals for I gamma, the involute of gamma, are the same as the tangents to gamma. Therefore, if you take the envelope of the normals of the involute, it is the same as taking the envelope of the tangents to the original curve, but the envelope of the family of tangents to a curve is like precisely that curve. Therefore, if you take the involute and then you take its evolute, you will get back the original curve. Okay, so it's very clear from a geometric point of view. All right, but you can also write it out from an analytic point of view. So if you write it out from an analytic point of view, what will happen is that you have to calculate the evolute, okay, of this I gamma. Okay, and if you do it using this expression, what is the evolute? The evolute is basically you have to the evolute of a curve is you first take the point on the curve, position vector of the point on the curve, and then move along the geometric normal by a distance which is equal to the the magnitude of the reciprocal of the sine curvature. Okay, mind you, the reciprocal of the sine curvature is the radius. The magnitude of the reciprocal of the sine curvature is exactly the radius of curvature. So you go to a point on the curve, and from the point on the curve, if you move towards the geometric normal, which will point towards the center of curvature, if you move by the distance exactly equal to radius of curvature, you will reach the center of curvature. So this Ei gamma is actually I gamma plus I have to move along the radius of curvature of I gamma. So I will call this as so which is 1 by modulus of k sine curvature of I gamma. Okay, this is the length I have to move. Okay, and then I have to and in what direction should I move? I should move along the sine normal. Okay, I should move along the geometric normal. Okay, I should move along the geometric normal. So I will just write geometric normal, geometric unit normal to I gamma. Okay, and of course the way this is written is as we have already done. This is I gamma plus 1 by now with the, if you remove the modulus in the denominator, then you have to put the sine curvature. So I mean the sine unit normal. So I'll have to put this, and then here I will write n as cap I gamma. Okay, this is what I get. All right, this is the formula for the evolute. But you see, now you substitute this. You see, what is the sine curvature of I gamma? What is the sine curvature of the involute? So you see, at this point, you see the sine curvature is what you have to move along the normal direction, all right, and you can see from the picture that the the radius of curvature is L minus S. Okay. Now this is something that is geometrically clear, all right, but you have to you can verify it again. So this if necessary you use the Frenet-Serret relations. So L minus S will be the the radius of curvature of I gamma, okay, and its reciprocal will be the magnitude of the curvature, okay, and since the you see the normal is pointing outward, okay, you have to put a minus sign to it. Therefore, what will happen is that you will get, so let me write this here, Ks sub I gamma. This will be it will be minus 1 by L minus S, okay, and that is and you have put the minus sign because you see this this the sine curvature is pointing away from the geometric normal, right, and basically at this point for the involute, the center of curvature is actually here on the original curve, and that essentially therefore the if you take the locus of the centers of curvature of the involute, you should get back the original curve, okay. So this is something that you can also check using Frenet-Serret, okay, by differentiating this expression if you want, okay. But anyway, so you plug this in here, what happens is that this becomes, so this will be equal to I gamma plus, you see I will get minus 1 by L minus S, okay, and you see ns hat of I gamma is something that I already written here. Ns hat of I gamma is T cap gamma, so this is going to be T cap of gamma, all right. And but what is I gamma? So I gamma here is the expression of for I gamma. Let me plug it in. So I will get gamma plus L minus S. Yeah. So I should put. I need to put a minus 1 here. Yeah. So so this I gamma value needs to be plugged in from here. So I will get gamma S plus L minus S T cap gamma, okay, plus I have this term, this will be minus of L minus S T cap gamma, and you see these two guys get cancelled and you get gamma. So you see the evolute of the involute of gamma is always gamma, and this is irrespective of whether what you irrespective of your choices for P naught and L, okay. So you take a curve, you take any of its involutes, then take its evolute, you will get back the original curve, okay. And this expression for the sine curvature can also be gotten by actually differentiating this, all right. And the thing that you have to worry about is that when you write whenever you write the evolute like this, okay, the evolute is parameterized in the parameter that you are using is the unit, it is the arc length of the original curve, it's not the arc length of the evolute. Therefore, when you write something like this, an expression for the evolute, it's not unit speed parameterized. You have to be careful about that. Yeah, it depends on the picture. It will depend on the picture, except that what did I do here? In the way I have drawn it, my original curve has negative sine curvature, and my both are negative. So that is what I was going to come to next, okay. So they should have the same sign. So in this case, the way I have drawn the picture, you see the sine curvature of the curve is negative and the sine curvature of the involute is also negative, okay. If you change the picture, both of them will become positive, all right. So that is very, very important. Yeah. So this is to show that you can write out these Frenet-Serret relations, and then you can actually analytically prove that the the evolute of any involute is the original curve, okay. And as it is very, very important, the sine curvature of the involute and that of the the original curve, they have the same signs. Okay, that is something that you have to remember. All right, so that is one thing. Then okay, so we come to this. We come to the next question. You see, so what we have seen is you start with the curve. You can take you can take an evolute. That is one thing you can do. There is only one way you can take the evolute, because the evolute is uniquely defined. It's just the locus of centers of curvature. The other thing you can do is you can take an involute, and there are many ways to take the involute. Okay, so taking the involute gives you several curves. Okay, but taking the evolute gives you only one curve. Okay, but you see, so the question is, if you take several involutes of a curve, how are they related? Okay, there should be, so what we have seen is that you take a curve, take its involute, any involute, and then take the evolute, you get back the original curve. That means you start with the curve, you take all possible involutes, then for each of those possible involutes you take the evolute, you get back the same curve, which is the original curve. Okay, so any curve is the evolute of any of its involutes. Okay, so that the fact that all these involutes are having the same evolute, that should be something special for all the involutes. That should be a special property, and that property is the fact that all these involutes, they are all parallel curves. They are called as parallel curves. Okay, so so I want to say that so you can ask the following question. You start with the curve, take its evolute first, okay, and then take various involutes. How are the various involutes connected to the original curve? So the fact is that there is at least one particular involute which will give back the original curve, but other involutes, how are they related to the original curve? They will be what are called as parallel curves. Okay, so I have to, so this is to motivate the need for, what are the idea of parallel curves, which is supposed to generalize the idea of parallel lines. See, parallel lines will have the same normal. Okay, and they are at a constant distance from one another. Okay, similarly, if you want if for a circular for a curved for a curved object, if you take for example, the simplest case is of course a straight line, zero curvature. Okay, and parallel lines are of course parallel curves in that sense. Okay, they all have the same normals, and they you take any two parallel lines, they are at the same distance, normal distance from each other. Okay, now if you take circles are the next case where you have non-zero constant curvature. Then parallel curves to circles should be concentric circles, because they will have concentric circles are the circles that will have the same normals as the original circle. Okay, and they are at a fixed normal distance from the given circle. All right, so you want to make sense of this for an arbitrary curve. Okay, so what you do is that the idea is very simple. You take an arbitrary curve and then you fix some distance by which you want to move it. What you do is you draw a new curve whose points are gotten by taking the points of the original curve. You move along the sine normal, that distance, and you reach the other point. Okay, so this is how you get what are called as parallel curves. And then the big deal is that all the involutes, okay, of a curve, they are all parallel curves. Okay, so let me make the statement. I have seen, you start with the curve gamma, you take any involute, and you get I gamma, then you take the evolute Ei gamma, and this is you get back gamma. Okay, but you start with the curve gamma. What you do is you take the evolute, you get E gamma, Okay, then what you do is take any involute. I.e. gamma. Okay, the question is how is this related to gamma? Okay, so the answer is that all these involutes are parallel curves and one of them is gamma. Okay, so then all I.e. gamma are parallel to one another, and one of these is gamma itself. Okay, so if you take the right involute, you can get back the original curve. Okay, so we need this idea of what is meant by parallel curves. So let me tell you about that. So you see, you start with the curve gamma. Okay, so gamma equal to gamma of s, unit speed. I don't need probably I don't need unit speed, but let's assume that. And so the idea is that you take a lambda, let us say positive, right? And what you do is that you define gamma translated by lambda. Okay, okay, and gamma translated by lambda is the following. You take any point here, this will be gamma of s. What you do is that, at this point you have the tangent. So this is t cap gamma of s. This is the unit tangent vector. Then there is a unit normal. This is n cap s sub gamma. Okay, what you do is that you travel this length lambda from this point gamma of s along this signed unit normal. Okay, you travel this distance lambda, so you end up with a point here. So you can, as you can guess, you will get a curve like this. Okay, and this will be, so if this is gamma sub lambda. Okay, and this length is your lambda here. Okay, so let me write it here. Okay, so basically gamma sub lambda is gotten from gamma by translating by the length lambda along the normal directions. Okay, and so you know how to write this point. So this point will be, you start with gamma s and then you move distance lambda along the sign normal. So it's going to be simply gamma, so it's going to be just equal to, if you write it out, let me write it here. So you'll get gamma sub lambda of s is gamma of s plus, you see, lambda times ns hat sub gamma of s. Okay, this is how the this is the curve parallel to gamma. Curve parallel to gamma translated. So translated is a very bad word. So I should, let me say, at a distance lambda from gamma. Okay, so now you see, and so if you take a curve like this, okay, then you can see certain things. You can see certain things immediately from this picture. For example, the way I have drawn it. So you see, the one thing is quite is quite obvious. Namely, if you had taken lambda negative, okay, then you would have traveled in the other direction. So you would have got a curve like this. You would get something like this, and this will be gamma sub minus lambda, and basically you would have traveled this distance lambda in this direction. Okay, right? And now you see that as you vary lambda, okay, you are getting this family of curves. which are all parallel curves to the original gamma. Okay. Now so that is one thing. From this picture, you see something is clear. Namely, geometrically, you take a point on the original curve, and you take the corresponding point on the parallel curve. You see the sine normal and the unit tangent, they don't change, okay, by definition, okay, because you see what you have done is, if you take this curve here, so I start from this point and I move to this point by this length lambda, okay. So for this new curve, if I draw the unit tangent, okay, the t cap gamma sub lambda will be the same as t cap gamma, okay, it is all right. And then if you draw the unit normal to that, the sine normal, okay, then you will see that ns hat of gamma sub lambda is the same as ns hat of gamma itself. Okay, so you are not changing the literally the Frenet-Serret frame. Okay, and now so there is something that's obvious from this in a geometric kind of way. You can see immediately that all these curves, okay, they will have the same evolute. The reason is because you see, what is the evolute of a curve? The evolute of a curve is the envelope of its normals, okay, but all these curves have the same set of normals, right? And therefore all these curves having the same family of normals means that for all these curves you will have the same envelope for the family of normals. That means all these parallel curves will have the same evolute. Okay, so geometrically it is very clear that all the all the parallel curves will have the same evolute. Okay, geometrically it is clear that all parallel curves to a given curve, let us say, have the same evolute, since they all have the same family of normals. As the original curve. What I mean is the given curve. Okay, so and what is another way to see this? The other way to see this is that, you see, take this expression here. So you are getting, you see, gamma sub lambda s is equal to gamma s plus lambda times ns hat sub gamma of s. Okay, now you do d by ds, okay, and which is d by ds, which is the same as applying dot. So I'll get gamma lambda dot of s is equal to gamma dot of x plus, see, I differentiate this with respect to s, then lambda is a constant, so I'll get lambda ns cap sub gamma dot of s. I'll get this, okay. But you see, if you so I want to write yeah, so you I want to calculate the curvature, okay. So what I'll do is I'll differentiate once more, all right. I'll get gamma sub lambda double dot of s is equal to gamma double dot of s, okay, plus again I'll get lambda. So see, ns hat sub gamma dot, I can use the Frenet-Serret, okay. See, ns hat sub gamma dot of s is by definition is T dot is Kn and N dot is minus Kt. So it's going to be minus Ks sub gamma of S into T cap gamma sub S. Okay. Therefore, what I'll get is so I'll have a product here. I would write d by ds of this term here minus Ks sub gamma of S times T cap sub gamma of S. Okay, and this is Frenet-Serret. Okay, so this is going to be gamma double dot of S, and so this is lambda. Here I will get, so if I differentiate this, mind you, there is a scalar function and there is a vector function. I have to differentiate both of them. I have to use the product rule. So minus Ks sub gamma of S, I differentiate the second term, I get T cap dot gamma of S, plus I keep the second vector constant, second term which is a vector constant, and I differentiate this minus Ks, and I will get, maybe it's better to put the minus outside. Okay. And then I will get Ks gamma dot, okay, of S. Okay, I'll get this. Okay, and mind you, so this is gamma double dot. So I want to say, mind you, this gamma double dot is the same as T cap sub gamma dot. Okay, so this is just, if I write T cap sub gamma dot, and I will get in the inside, I will get in the bracket, I will get 1 minus lambda times Ks sub gamma of S. Okay, that is these two terms combined. All right, and then there is this other term that is left, which is going to be minus lambda Ks dot gamma of S, T cap gamma sub S, and then so I want to say, I use this T cap dot gamma can be written in terms of Ns. So I want to say that see, the point is that this gamma sub lambda is not unit speed parameterized, not necessarily unit speed parameterized. I would like to calculate the the curvature of the parallel curve. Okay, so K sine sub gamma lambda of S, its modulus is, at least you know the formula, it is norm of gamma sub lambda of S dot cross gamma sub lambda of S double dot divided by norm gamma sub lambda of S cube. Okay, you will get this. This is this is the formula for curvature for a general curve which is regular but not unit speed parameterized. Okay, you apply this formula. Okay, and then what? So if you apply this formula and use the Frenet-Serret, okay, what will happen is that you will get this expression. So let me write out this expression. So let me leave it to you to write it out. So you will get this. You will get that the sine curvature of the parallel curve, okay, is the sine curvature of the original curve divided by modulus of 1 minus lambda Ks of S. Okay, and from this expression you see that this denominator should not vanish. Therefore, to define the parallel curve, you need the condition that lambda times Ks gamma should not be 1. That's very, very important. All right, and you can see that from here. You can also see it from the picture. Okay, if you draw a picture, but this condition is important. And the other thing is that you see this, the sine curvature of the parallel curve and the sine curvature of the original curve, they have the same sign. That is also obvious if you look at the way that the parallel curve is defined. Of course, wherever I am defining the parallel curve, mind you, I do not want, I want its sign curvature, not to vanish. Okay, so I will always assume that sign curvature is of the same sign. Okay, so one important condition is that you need this to define the parallel curve to a given curve. You need to choose this lambda, so that lambda times this, so I should write lambda times, this should have been ks. Okay, so this is very, very important. Okay, this is an important condition. So, so let me write it out here. So I will leave it to you to write out the, to write this computation. You have to take the cross product of this and this. Okay, and you will get here modulus of ks sub gamma of s divided by modulus of 1 minus lambda ks sub gamma of s. Okay, and k and without the modulus, these two will have the same sign. So ks sub gamma lambda of s is equal to ks sub gamma of s divided by modulus of 1 minus lambda ks sub gamma of s. Okay, so we need to assume that ks gamma is throughout is non-zero throughout positive or negative, and that lambda is chosen so that you see lambda times ks sub lambda ks sub gamma of s is not equal to 1. Okay, this is an important condition. Okay, and see, once you do this, it is now clear that the saying that all the involutes have the same evolute is the same as saying parallel curves have the same center of curvature at every point. So that is also something that you can check from the picture. So you see, if I start with the curve gamma like this, I have this point here. Okay, so this point is gamma of s. Okay, then how do I get the parallel curve? I draw this. At this point I have the sign normal, and I move this distance lambda here. Okay, and I end up with this gamma sub lambda. So I get this point here. Okay, and so this point is gamma sub lambda of s. All right, and I move in this direction. Right, now what is the center of curvature of gamma sub lambda? Okay, so I have to move I have to move along this direction. Okay, and the distance I have to move should be equal to the magnitude of the reciprocal of the sign curvature. Okay, so how much distance do I have to move? I have to move by this distance. Okay, this distance is what we have calculated. I have to move by this value, and mind you, the sign curvature is negative. So the distance I have to move is minus ks sub gamma of s divided by 1 minus modulus of 1 minus lambda ks sub gamma of s. Okay, all right, and and in this case you can see that moving this distance here is the same as moving this distance here. Okay, which is the right distance that you require to move to get to this center of curvature of gamma. If you make this calculation, you will see that the center of curvature of gamma sub lambda and the center of curvature of gamma, they are the same from this computation. You can check that. Okay, so I will stop here. I have to go to the. Okay, so I'll leave it to you to verify these facts. Okay.